Okay, so today's topic we want to discuss are mass balances. And so mass balances is an important concept that comes up a lot in chemical engineering, but also in things like mechanical engineering, civil engineering, biological. Basically anywhere where you have some sort of materials moving from one place to another, we use this concept of mass balances. And the basic concept behind those is that we have some sort of black box type thing that's a mixer or a boiler or a distillation column or a separator. Just some sort of black box where you've got flow coming in from one or more streams, and you may have flow, and then you've got some flow going out. And the key that makes these mass balances work is the law of conservation of mass, which says that the sum of the input into our system has to be the sum of the output out of the system, wherever we've defined our system. The key assumptions we're going to make with regard to this are that there are no chemical reactions going on at this point, and that there's no accumulation. In other words, there's no material building up here. Whatever we put in has to come out, so that it's a zero-sum game. As you get deeper into doing this in higher level courses, you'll find that those things can become a factor. But for this course, we're going to keep it simple. So one of the things we can do is write, if we had a diagram like this, where in this case we have A and B are inputs, A, B, and C are inputs, and D is an output, that we know that the sum of the things going in has to be equal to the sum of the things going out. So we can write an overall mass balance that tells me that the sum of the inputs, so A plus B plus C, must equal D. And that can be a useful concept if I knew enough about the three parts there. In addition to an overall balance, some problems might have to where we have broken the stream down into different components. For instance, let's say this is made up of this stream A is made up of 10% X and 90% Y. Stream B is all Y, it's 100% Y. Stream C is 5% X and 95% Y. And what we want is stream D to come out at 8% X. And so we can do component balances on just X and just Y and use those equations to also help us solve things. So let's write the one for X. So if I were to write a component balance for X, I would just take the percent of each stream that is X and multiply it by the flow rate of that, or the amount in that stream. So stream A is 10%, so 10% of A is X. 0% of B, because it's all Y, so it's not written here, but we can imply that if it's 100% Y, that also means that it's 0% X. So 0 times B, so that's going to actually end up going away. 5% times however big C is, and now my end solution is that I want 8% in D at the end. So I could write that balance, and that would give me two equations. And then I could actually write another one with the Y balance. So to get the Y balance, 90% of A, 100% or all of B, 95% of C, and it's not written here implicitly, but I can figure out that if it's 8% X and all the rest is Y, 92% of my remainder is Y, so 92% times D. And so from the looks of this, it would look like I have 1, 2, 3 equations, and I can write 3 different equations. But the other thing to realize is that these 3 equations are not independent, because if I just added these 2 equations together, I would arrive right back at the overall balance. If I added the X and the Y, I get 100% of A, 100% of B, 100% of C, and 100% of D. So a key characterization to realize when you're trying to solve this and you're needing to solve a system of equations is that this is really only two independent equations, which means if I were trying to solve for three variables, I would need some other equation that related things. And so certainly here, if I were trying to solve for all four variables, A, B, C, and D, I need at least two other pieces of information. But my goal here is not to solve this question, it's just to show you how these things would set up. And if you had additional components within the streams, if there were also something Z that was some percent of this, that would be an additional one. And so that we could write. And so for every, I can write an overall balance and one for each component on a device. And so for all the questions we'll work with today, we're going to work on just one system. Although again, you can expand this and you could have multiple items, but we'll discuss that in a different video. But the key that I want you to get out of this video today is just that the law of conservation of mass tells me that everything that is put, the sum of the streams that are in must be the sum of the streams that are out. And this works for either if you've got flow to where you've got some sort of flow in minus flow out, or if it's all put in there at the beginning, it all has to come out at the end as a batch process. But either one of those, this is our main thing. The assumption we make is that there's no chemical reactions and that there is nothing collecting inside our tank or whatever we're doing. And that's how we can write balance equations.